Hello, everyone. Welcome to the Pinnacle Academy Technical Panel. I am Sannel Patel, the Director of Business Development and Marketing at Pinnacle Ozone Solutions and a chemical engineer. I'm thrilled to be your host today for the first Pinnacle Academy section, which we will discuss ozone and advanced oxidation processing, also known as AOP. This section is going to be part of our Pinnacle Academy series, where we bring together industrial leaders who are not just shaping the future of water technology, but also improving and redefining the possibilities of innovation and science. Today, I'm honored by two distinguished experts, Dr. Saad Jasim, who is the president of SJ Environmental Consultant, former director at Industrial Joint Commissioning, editor of Ozone News, and past president of International Ozone Association. He's a pioneer in municipal ozone applications, as well as led groundbreaking work in toxin removal and advanced disinfection. Welcome. Thoram Chandra as well, who is the Chief Science Officer at Pinnacle Ozone Solutions with 3 decades of R&D experience, including leadership roles at Walt Disney as well as Guardian Manufacturing. Tom has been instrumental in developing ozone systems across various applications and environments for precision ozone demands. Thank you both, gentlemen, for joining us here today.
Absolutely.
Thank you.
So starting with you, Dr. Jasim, you led Windsor transformation to ozone drinking water applications years ago. You were convinced ozone was the right technology. What has changed? Can you tell us a little bit about your thought process about including ozone into that application?
Well, when we started, we did research, and that is, in fact, what I emphasize always. You need to study first what are the challenges in order to focus what technology could be used. And the decision wouldn't be just upon literature, because it's always a site specific. And that is what we did. And the application was on the use of ozone for the water supply, which was Detroit River water. And Detroit River water, Detroit River in general, is considered one of the areas of concern for the government of Canada and United States under the water quality agreements and as part of the International Joint Commission. So it is an issue because of the industry on both sides between Canada and the United States, especially Windsor and Detroit with a lot of industry. So, and one of the things we were facing in the early 90s was the problem of taste and odor. Mm-hmm. And because of, the warm weathers, also zebra mussels cleaned up the St. Clair, the Lake St. Clair. And so we start to see this problem, a lot of cost using powder activated carbon and this is, it's a hit and run, as they say. It is potentially, once you stop, if you get a hot weather, and we had it one time in 97 in October, and suddenly we had 2-3 weeks of sun and warm weather, and the odor came back. The eastern odor came back. And guess what? They don't have powder activated carbon on site. So by the time you get it, and at that time, I was still working as a consultant with them and basically working on the pilot study. And I said, we have to get it, even it's October. So they rushed powder activated carbon and comes a slurry. And of course, when you rush something, you need it overnight. The cost will be way higher. Mm-hmm. So that is what, when I took over in 98 at that time, the title was Superintendent of Water Production. And so I continued the investigation. In less than a year, I put a proposal to the commission. And at the same time, I was doing my own investigations, not as just part of the, because we looked at disinfectant byproducts, reduction of chemical use, optimization. But I looked because as typical situation, the intake is downstream of sewage discharge. And that is always, and this is not the only one. There are many places. In my investigation, I looked at the city of Detroit, other cities, the same situation. So I start collecting samples, and you don't go and select samples when you have beautiful, nice day, calm, and all that. No, you select the samples when there is heavy rain,
right,
and storms, and I get some scary results. And I had the samples analyzed by a certified lab, certified microbiological lab. We get up to 600 oocysts of cryptosporidium per 100 liters.
wow,
And
wow.
500 something cysts of Giardia per 100 liters. And it's not like once, few times, 300, 500, 200. It's scary.
Yeah,
And
yeah.
basically, it depends on your luck this way, because we were using only chlorine, which doesn't do anything to that. So we were lucky so far. So at that time, I took over in August 98. In April 99, I put I asked to meet with the commission, and because as a manager of a water plant, you don't meet with the commission, only chief engineer and the commissioners, and the general manager and the mayor. So when I met, I said, "Okay, this is the situation." I took them by surprise in a way, and the mayor asked a question. This is again 1999 April. He said, "What?" And he is a lawyer, the mayor. He said, "What are the consequences if we don't use it?" A typical legal question.
Mm-hmm.
Well, I said, a good example is city of Milwaukee.
That's right. That's right.
93, I said, 100 people dead, 400,000 people were sick. Many people haven't heard about the issue of Milwaukee. I was one of the people who went to the meeting at Purdue University in Indiana that organized by the EPA in 94, because they said it's too sensitive to do the meeting in Milwaukee. So they did the meeting in Indiana to tell us about the issue of the water quality and the problems. And at that time, they were asking somebody to come as a water quality manager after 100 people died, And guess what? A Canadian went from Calgary, Kerry Lewis. I'm sure you guys know the name. And so anyway, so I told him this is the situation. And I said, after 6 years, and it was reported, after 6 years, the city still have 2,000 lawsuits. And that is a scary thing you say to a lawyer, Yeah, so, but he was right in his question, basically. He wants to see, or is it like somebody complain on the phone only? But when people die and that. So he said, okay, I want a detailed report, financial, timeline, all that. So we came back in July. At that time, the meeting was indicated in 2 months. So by the time, beginning of July, we had the meeting. And there was some resistance. And usually there are people who don't like change. And that's typical. And nobody died. So why do any change here? So, but you don't wait until someone dies.
Right.
So the commissioners supported. The administration was a little bit, I would say, negative on the application, but the commissioners unanimously and the mayor supported the application. That was July 99. So we were doing the construction at that time, like established the RFPs and all that. In May 2000, an incident happened in Walkerton, Ontario. 7 people died because of E. coli. And it's a small town of 4,800 people. 2,300 were taken to hospital, half of the town.
Wow.
Yeah, and 7 people died, E. coli and Campylobacter. So, and that shifted the negative look of spending money to get a new, everybody like, oh, we're waiting for ozone. So when we applied, it came online June 15, 2001. That was the first city in Ontario. Before that, I'm sure you all know the name, God bless his soul, Kerwin Rockness.
Yep.
Kerwin and I, we met a few years before, and we established some good professional relationship and discussions. So we jointly went to other locations to give seminars about ozone. We went to the region of Halton, and the managers and the operation guys came, and about 30, 40 people attended the event. So we gave them about 2 hours, 3 hours discussions and seminars, the advantages and all that. And that was before we start the application, but we used the historical data. Once we started, and Kerwin and Glenn Hunter, we worked with us to do the control system and all that. After we started in 2001 and successfully, and people see, and it was the middle of summer, we eliminated powder activated carbon. Beautiful taste for the water. People celebrated for that. We did an event at the plant, so it was good. Like you use the science and politics together. So the region of Halton, they decided 2 plants to use ozone, which was Burlington and Oakville. And they started, and we brought their operators, we trained them on site. So that was starting a good collaboration with others. After a few years now, 7 cities followed what Windsor did, which is good. And they see the advantage. And also what we did an evaluation. What are other issues like we are looking at? We started in 2002 looking at pharmaceuticals removal. We were, I think, the first municipality to look into that. And we compared what is conventional versus ozone. And we had a peer-reviewed papers published on that, and shows the data, excellent data has been that. And also we did another study on reduction of cost when you use ozone. And also I'm an adjunct professor at the University of Windsor, so I had one of the students coming to work on the pilot plant, the one I built in '92. So, and we compared the data the year before and the year after ozone. And we were saving $247,000.
Nice.
So, and that was also a peer-reviewed paper, and also that's been mentioned in the paper that published in 2020 by a group of the Ozone Association members. And that table was included, and shows we were saving about $4.55 per million liters. At that time, we were pumping up to 300 million liters a day in summertime. So made a big difference.
Yeah.
So that is what the thing is. But the advantages we start looking at, I didn't say, okay, we did it, that's it, let's settle. I start looking at other issues, how to control it further, the disinfection byproducts. And we were successful in showing the data, the pharmaceuticals.
Thank you so much for that explanation. So, Tom, coming to you on this, right? You have tons of experience on designing industrial ozone systems to municipal plants. Can you walk us through like how you, what is required in an ozone system, and like how you go about with and what applications you look at, what type of parameters that need to be looked at to design something that is actually a high quality ozone system at the end of the day?
Yeah, I think where I come in is the ground floor, like the very beginning. The ideal scenario is the client comes and they have a problem they want to solve. Sometimes it's traditional, like in municipalities, it's disinfection or color or taste and odor removal, like Saad was saying from the other systems he employed, which Ozone is extremely good at. Sometimes it's manganese and iron removal. Or sometimes it's disinfection credits. Other times it can be for pre-oxidation of TOC, the total organic carbon, so that you can get reduction in disinfection byproducts when you post-chlorinate. So first thing is, I ask when the client is, what's the purpose? What they're trying to achieve. When our salespeople bring them in, the samples that come in, I often will get samples coming into the lab to answer the next question, which is number one, how much ozone do we need? A big question. Sometimes the question would be, is it effective? We do get samples from industrial processes, and these are non-typical. They're atypical a lot of times. There's certain organic chemicals that are caused, or wastewater from industrial processes. Sometimes it could be pharmaceutical waste. It could be industrial waste. There's different types, and so those systems we have to really kind of look at it on a chemistry basis to see if this will work. So it can be pretty complex. Usually, if it's a simple system, like municipality, then we know what we're doing. I know it will work. And the question is, how much ozone do you need to accomplish your target, your reduction in either disinfection or color or so on? So then if it's that, we'll get a sample in our lab, and then I'll do what we call an ozone demand decay on that sample. So I'll empirically determine based upon hopefully the worst water quality sample they have. Like Saad said, it can change throughout the year. So we try to get something that's representative of a worst case. And I'll do ozone demand decay in that water. And we can get really technical in another discussion how I do that. But basically, I dose it very accurately, and I measure the instantaneous decay, or the demand rather, and then the following decay from that. I find the half-life, and I figure out how long the ozone lasts, and I get that half-life from that. Also, I get the post chemistry, so I can say, yes, it did achieve its target based upon this dose, and then we'll use that as a basis to design a system and scale from there. The next step, ideally, depending again on the complexity of the project, would be the pilot scale. And sometimes that's necessary. In some instances, not. And sometimes it's a fairly well laid out process, and we know what we're doing, and we can go right from there to full scale design. Some systems, and these are client dependent, some of them want to prove it at their plant. Even though you can prove it somewhere else, well, our plant's different. Our plant's special. So you got to prove it here. And a lot of times it's just because they need to see it themselves, and get empirical proof that, yes, this works, and they get the confidence for that process. And also can answer certain questions that we just can't answer on a bench scale, one time. You really need some real-time water quality changes, and how do you address those in real time. So a pilot scale would be next. And so we design a pilot scale based upon what I got on my benchtop data, put it together, and then we run that usually sometimes either through our company only, or with the client directly, or with the consulting company. Yeah. So we run that pilot scale, and we may get some changes in design based upon what we understand from that pilot scale. But we basically refine the process from there, answer any questions we have. Then based upon the parameters from that pilot scale, we'll use that to use it for the large scale, scale it up to the big system. Yeah.
And you spoke about the ozone system and designing that. Thank you for explaining that. But can you explain? So I know the ozone system takes oxygen from the atmosphere, or LOX, and then converts it to make ozone. Can you talk us a little bit through that process?
Sure.
What is required to produce ozone?
Yeah. So all our systems and all the ones that Saad works with and I work with in the industrial level are oxygen-fed systems. And that's the reason being is that with air, you only got 21% oxygen by volume with air, and so there's a limit to how much ozone you can make from that. There's also certain design considerations that can happen from that. Nitrogen being 78% of that. If any moisture occurs, you'll form nitric acid, and that nitric acid just could totally destroy your ozone system. And just not worth the production. The amount of gas you would have to feed in order to get the same amount of ozone from 99% pure oxygen versus 21% is significant amount of difference in gas volume. So we don't deal with anything with air-fed systems. Those are usually very small, sometimes on spas and pools and things like that. Some of those will have a place for that. So all of ours are oxygen-fed. So the first thing is your source of oxygen gas. And there's really three main ways of making oxygen, or having oxygen sourced to your generator. The first two ways is we actually are extracting that from the atmosphere. There's PSA, pressure swing absorption, or VSA, vacuum swing absorption. And both have a place depending on the sizing of that. But for right now, we are pretty much focused on, pretty much all our systems are PSA, pressure swing absorption. What that takes is a special bed or molecular sieves, like little small beads that are in a bed, and they happen to be, when they're pressurized, they absorb the nitrogen gas, and that's oxygen passed through. And there's two beds, so it's cycled in such a way that when one bed gets saturated with nitrogen, it kind of has a timing down, and it'll switch to the other bed, and it'll blow off when the pressure releases. The nitrogen releases away from the sieves and goes to exhaust and exhausted outside the system, and then switches back and forth, back and forth. And your net effect is that you concentrate the oxygen from 21% to typically 93, 94% pure oxygen in your supply from that. Okay, there's a little bit of nitrogen left over, a little bit of argon, a little bit of CO2 in there, and no water, of course, all water is removed as required. It has to be very, very dry. So that's one source. Depending on sizing and different considerations, we'll go to LOX, liquid oxygen, as the other source for the O2. And that, of course, has its benefits because it's right there. You just have a big many thousand-gallon tank, and you have a service that come refill it at certain periods of time, and you have this nice feed of LOX. That's most common for municipalities because they use a lot of oxygen. So LOX is most commonly used for larger systems. Okay. So once you have that oxygen feed gas coming in, 93% or 100% oxygen, that's fed into the ozone generator itself, the heart of the system. For us, we call it the plasma block, but basically it's a coronal discharge system or a plasma system. And there's a lot of design considerations of how to do that the best way. And that's what sets different companies apart. It's really very technical to do that well. You can make ozone very easily. I mean, you can just put two sparks together, you can make some ozone. But to do it really well, in order to be highly efficient, in order to make as much use of the electricity, which is cost, to convert that into ozone as efficiently as possible, is really where the technology comes in. And also do it reliably, and also do it with full control. And with the plasma block systems, the ability to control that ozone is extremely important, because that's important downstream when you want to modify the amount of ozone you generate based upon a response from a sensor of one type or another to achieve your processes. So be able to control the ozone output accurately in from 0 to 100% turn down is very advantageous and very important, and be able to rely upon that. So the ozone generator within the cell, just to be really brief, and this is just, ozone 101, right? It's really, it's basically you're passing ozone gas through a very narrow gap. And the gap is really super important. And that gap can be, in tenths of millimeters. So it's a very narrow gap. And you have two electrodes with the spacing of a dielectric, like a ceramic plate of some type, but basically a dielectric that basically causes the between the anode and the cathode of these two plates, which are at a very high frequency and a very high voltage, instead of making sparks like lightning bolts across the two plates, as you might imagine would occur, it creates a plasma field, a coronal discharge field. And that dielectric plate makes that happen. And so when you have this intense electrical field going across these oxygen atoms as O2, it will break up the O2 to singlet oxygen. That's like 1O1. That single oxygen is very reactive and will bump into another O2 and combine itself to make O3, which is our ozone. Okay, it's very complex reactions that take place in there because you're also creating and destroying them at the same time. But you have a process where you're making more than what's being destroyed, and also the heat that's created from that, which is the enemy of ozone in production. You have to have systems that remove the heat very quickly. And so this small gap is really good for that as well, because small spaces, the high surface area to volume ratios, all this stuff comes into play to remove that heat as fast as possible as you're generating that ozone. There's all kinds of things about frequencies. The one thing with the plasma blocks, they run about, I think, 22 to 23 kilohertz. So they're very high frequency. We don't hear that, unfortunately. So they're all near virtually silent, and run around, I think, from 3 to 5,000 volts or something like that in that area. So they're designed to be extremely efficient in creating this ozone through this narrow gap. So what ends up coming out from the end of the stream is usually 10% by weight ozone and about approximately 90% by weight oxygen. Okay, and the percent by weight is a critical piece of parameters and design that we work around, because that translates into a lot of things downstream when we get into the injection process, because of the volume of gas that we have to work with, and then the amount of ozone we can push into the water based upon the solubility function and so on of the ozone gas in the water. So after generating the ozone, we made the ozone. The next step is getting into the water efficiently. And this is where a lot of work is done through different companies that we work with, from our own stuff that we do in-house to, Maisie, for example, that designs the systems, and others, is getting that ozone to dissolve into the process stream as efficiently as possible, balancing out a lot of factors, balancing out pressure and flow rates, gas-liquid ratios, solubility functions, bubble size, and all this, and the amount of energy to do that in the most balanced way possible. Because in reality, you have to balance the cost, which is usually in size of pumps or electrical draw, amperage and so on, to equipment, to efficiency, and we try to balance all that out to make sure we get that appropriately and that it works right. In other words, we achieve what we want in terms of what we call mass transfer efficiency, generally 90 to 95%. We usually don't try to get higher than 95%. And because people ask that, like, well, why don't you get 100%? Why don't you do more than that? Well, it turns out, to get that extra 4 or 5%, it takes a significant amount more of energy to do so, and the payback generally does not equate. It just takes too much energy to get that extra 5%. Most cases. So therefore, it's not efficient, advantageous to try to capture that a few percent of ozone to try to get it all in. Only a few times. There are times we can get higher, but that's due to water chemistry. And water chemistry, the demand is so high that it would just pull that ozone and makes it easy. Okay, so when I talk about ozone, we have gas preparation, which is a critical piece of it, because you got to have good gas preparation, making an oxygen really clean, efficiently, either via PSA or LOX. That's extremely important. Clean gas, clean piping, all that feeding your generator. The next piece is your generator itself, making the ozone efficiently, reliably, with turn down ratios, great controls, safety, and all that. And then the injection part. And all that comes together, for your process, and all that's designed to achieve what you want in your process of disinfection or target contaminants, pharmaceuticals, all the different things that we wanted to do.
Let's move into more of a discussion on where ozone is moving forward in terms of AOP. So, Dr. Jasim, if I can ask you this question, you've published and consulted on a lot of projects from toxin removal, algae removal, and there's been a lot of challenges that come around that. But how do you see AOP, like the use of ozone and hydrogen peroxide or ozone and UV, how do you see that moving forward in real world applications?
Well, I think the opportunity for ozone to have a good application, and we were looking at now with the cyanotoxins, what happened in Toledo in 2014, 11 years ago. There are certain toxins identified, and they were not before in the EPA guideline or in Canada's guideline. And we have the microcystin LR, and now we included the toxin A and the cymdospermousin. So we did originally some studies on it back in between 2017 to 2020, and we were able to see the success of oxidation of these based on the water quality in the Great Lakes and its tributaries. The ozone was dominant. The ozone dosage was the key issue. There is a pH impact as well, temperature and all that, but the dominant was the ozone dosage. And we're not talking about high concentrations. So, but then we look at it because we looked at individually each one to them. We looked at the kinetics of the reaction, but those three, they come together. So we need to look at them together. So we looked at now, we have a project now I developed on the simultaneous oxidation and removal of the three toxins. And so, but we use ozone and peroxide as advanced oxidation at different pH, different temperatures. And we have we're developing some data to be published on that, and the project is going for the next 6 months. And we try to that the one of the problems we find is the funding for the projects.
Mm-hmm.
People do not fund projects until you have a problem, and that is, and unfortunately, and I say that, and I said it many times when I was president, before that as well, of the Ozone Association. The ozone companies, not as much, especially the large groups, I criticize them. They don't fund research as much.
Mm-hmm.
Why you see it in Europe is different. Here in North America, the UV industry, they are a great supporter to universities in that. Like I worked with the University of British Columbia, they have like 10 graduate students are funded by masters and PhDs from the UV industry.
Mm.
And I don't have a single one. I've been, since 96, I'm an adjunct professor. I could not get any funding. I have 7 master students I supervised with the University of Windsor, 1 master student with the University of Western, and 2 PhD students at the University of British Columbia. And unfortunately, there is a lack of funding. And we need the funding because we need to develop some grassroots, because we will be retiring eventually. Somebody has to take over.
Right.
And we don't have that many people. And you see that when we do conferences in North America, the number of students and universities are limited.
Mm-hmm.
They're applying to the conferences. You go to Europe, it's the other way around.
Mm-hmm.
And that is building a new generation, and we need to do that.
Mm-hmm. I agree.
Yeah, so thank you. So Thoram, if you can help us with, I know we've been technical, but I want to get the engineering part of me out here, and I want to talk about AOP and what type of performance does it unlock? Like, what is the chemistry behind that? If you can tell us, I know we've talked about hydrogen peroxide, we've talked about some acid usage as well. Can you explain a little bit about the chemistry behind that?
Yeah, sure. I mean, the whole purpose behind AOP is the generation of the hydroxyl radical. And the reason why is because it's the oxidation power in reactivity and reaction rate. And I've always kind of referred to the hydroxyl radical as the Pac-Man, of oxidation chemistry. I mean, it just reacts with everything. And so when we talk about reactivity, we have things that can be selectively reactive or universally reactive, and we kind of refer to that to different chemicals. So when we look at chemistry, we look at the kinetics and thermodynamics. And we always ask the question, is it thermodynamically favorable? If something's not thermodynamically favorable, it's not going to react. It just won't do anything. And then you have to ask, well, how fast? And that's the kinetics part. All right. So you can have a great example I like to have about this, and I'll move towards what we're talking about with radicals. It's like if you put hydrogen gas and oxygen gas together in a bottle, they are thermodynamically favored to become water, but there's what's called a kinetic hump. They just won't do it by themselves, right? So you have something that's thermodynamically favorable. They want to become water. It's more, less entropy. It's favored. Energy's given off. But you need a kinetic hump, meaning like a kinetic hump, like a spark, and of course you get your big bang, and that's really fun in the classroom a lot of times, and you make water. Well, the same thing with an oxidation chemistry. The thing that we're looking at is it thermodynamically favorable and how fast. Well, it happens to be that hydroxyl radicals are almost always thermodynamically favorable, and their kinetic rates are just extremely fast. Okay, when we talk about kinetics, we have the rate constant, that's reaction usually first or second order, and that rate constant site usually something times 10 to the 9th. Nearly instantaneous, very, very fast reaction rates. So the reason why we go for radicals is because ozone is slightly selective. Yeah, it's a great oxidizer and oxidizes many things, but there are compounds that it just won't react with. It's not either thermodynamically favorable or not, or the kinetically it's very, very slow. And what happens is that we have compounds that have these longer lasting, more stable organic compounds, typically with an electron withdrawing groups like the chloride on it or fluoride on it. It stabilizes that molecule to such an extent that even ozone can't attack it. They can't pull those electrons off. Doesn't have a strong enough electrochemical power, to use some regular terms, to get the electrons pulled off to break this molecule up. So when you bring in the hydroxyl radical, it has a much higher EV value, much higher oxidative power, and can pull those electrons off. Okay, there's only a few things. I think there's only really one chemical that's has a chemical higher than that, and that's pure fluoride. Fluorine, that's fluorine gas, I mean. Fluorine gas is like the king of electronegativity, the king of removing things, but it's way too toxic, we can't use it. So really the next best thing is hydroxyl radicals. Singlet oxygen is really, really close to it as well. So for AOP, what we strive to do is we actually have a mixed oxidation system where you actually have ozone doing what we call direct reactions, where ozone is directly reacting with the contaminant or the target compound of choice, and that will happen and do its thing. And then we have ozone reacting with something else to make hydroxyl radicals. Now, there's actually a whole field of understanding of how radicals are produced and how efficiently to make them. In natural waters with natural organic matter, NOM, ozone actually will make some radicals on its own without anything like adding peroxide or something else. It will make some levels of hydroxyl radicals in the background, but typically not a lot. But enough that can have some impact, but not usually for your target compounds that you really want to get rid of this recalcitrant organic chemical like a pharmaceutical or toxins that are resistant to ozone. So yeah, you add something to make more radicals, to really make a cascade of these radicals. So we add something like hydrogen peroxide as an example. You can also do with hydroxide ion. Hydroxide ion at a high enough pH will become have enough of the hydroxide ion around that it will react with the ozone molecule, creating radicals. And of course, UV react with ozone, we create radicals as well. For us in our industry, for the most part, we do. I would say peroxide is like the number one. Between peroxide and ozone is number one in my experience, anyways. I also do pH modification to make radicals as well if I don't want to use peroxide. So what happens is that ozone at a certain sweet spot, and I call this a sweet spot between the molar ratios of ozone to peroxide. You have this efficiency that you can make a significant amount of radicals by that reaction. And so we generally try to find this molar ratio between the two when we apply it to make sure we were as efficient as possible in the production of radicals. The ozone reacts to the peroxide, makes those hydroxyl radicals, and then those radicals attack indiscriminately, really, anything that can be oxidized by that radical. And the reaction rates are all very, very quickly. So there's no real half-life of any consideration, that not on the real world level, of the radicals. We call them those basically instantaneous. So you can have the very fast, short reaction times required for radicals themselves to do the job. And so that's the basis behind it. There's actually some finesse you can get into where I've done systems where actually I would do pre-oxidation with ozone without intentionally making radicals to let ozone do the bulk of the work, because you want your radicals, in my view, working on things that they need to work on, which is what ozone can't do. So actually, I'll design systems where I'll pre-ozonate, actually have a reaction chamber where I'm just ozonating, and ozone is doing its work. It's doing its direct reactions, doing the bulk of the oxidation that it can do. And then I'll have another chamber where I'm reozonating again, and then adding peroxide and making radicals there, and let the radicals do the job that they need to do in the overall scheme of the system.
Go ahead.
One thing, just to add to what has been mentioned, with the hydroxyl radicals, you need the ozone. Usually, most of the people put the ozone not for the pharmaceuticals, or that disinfection is the main thing. If you put it for disinfection, you don't want to put the peroxide immediately, because basically you're going to have ozone decay very quickly.
That's right.
And it's like a quenching agent. So you give the ozone to reach its target for log inactivation, and then with the peroxide. However, again, with the site-specific water quality, when we did the comparison in the cyanotoxins, we found because you look at ratio ozone to peroxide, 10%, 20%, 30%, depends on the water quality and what kind of molar things in the ions there. So when you do that, we found that not a significant changes because you're talking about nanograms per liter in these matters. So, if you can total removal of, say, 93% or 92% by ozone, is a removal an additional 1% or 2% of nanograms per liter, 2 or 3 nanograms per liter, worth to bring a new process. And that's why you evaluate it from engineering and cost evaluation.
That's right.
And that's what and plus, one of the challenges we have, as we know, like I worked for peroxide in the last 25 plus years, the shelf life. Like when you bring the peroxide, usually you don't bring 1 gallon or 2 gallons for a water plant. You're going to bring a huge containment area, so you have a tank. If you bring, say, for example, 50%, if you don't use that soon, within, say, 2 weeks, that goes down maybe to 30%. So you have to adjust your calculations all the time. So that depends on what you want to use and how much you want to remove. Like the current evaluation we have, the ozone and pH control also help. Like what I did in my studies is evaluate what pH control was better, and I went into the pH control with carbon dioxide. And the advantage is that when you do that, you bring the pH down, and if you use acid, you need to bring the pH up again because you can't send it to a distribution system. You will have a situation like what happened to Flint, Michigan. You'll have the leaching of lead and all that. With CO2, when we send it to the reservoir, in about 7-10 hours, and when you have huge reservoirs and like that, the pH goes up again because carbonic acid, when it's formed when you add CO2, start to decay into CO2 and water again.
That's right.
So the pH go up again. We introduced that back at the Water Quality Technology Conference in 1998. We presented it in San Diego at that time. And I put it in full scale in 99 because I had a lot of data in this. We started in a small pilot also. We did it on pilot plant, but then I did a small pilot on the full scale as well. And I worked with the manufacturers of oxygen and CO2, and they did that, and they were very supportive. And it's been used since 1999 for pH control until this day. So that is what I believe in pilot research to you reduce redundancy, you get exactly what you want. It's a good investment for to identify what problems you could face in your work, and that is what we do that. And you need to invest in technologies, like for example, how ozone is effective in removing particles. We did a particle count studies, and we looked at the size of GRG and cryptosporidium. And we found that when ozone is used, the removal of these particles 10 times more than what the conventional methods are.
Yeah, that makes sense.
And that is additional things of ozone application. That's why ozone provides with many benefits here.
Correct. Yeah, that's the microflocculation event that ozone does. That's been seen in the aquarium industry as well. We're using ozone for enhancing filtration using the salmon filters. They find that you get this microflocculation effect with ozone. Saad, I had a question with you.
Sure.
Can you talk about the importance of pH and peroxide and ozone reaction rates and how important that is between the two?
When you reduce your pH, your ozone decay is less when at a lower pH. And we did a detailed ozone decay study back in, I think, year 2000. And we looked at temperatures from 4 degrees all the way to 20 degrees and to see the impact. And we looked at pH reduction. Say, for example, the water coming at raw water at 8.1, we bring it down to 7.4 or something like that, because when you use alum, you're going to take the pH further down.
Right.
So we looked at different ways. So with the pH reduction, especially when you use ozone, it has an advantage. In fact, when we did that, in fact, before the ozone, it was because you will get an improvement in disinfection, because reduction of pH, especially at cold and temperature, the CT requirement is less compared to higher, at low temperature, compared to warm temperature. So your disinfection, it doesn't need to go sky high in order that. And that is a cost reduction when you use ozone. So, and based on different points of that you need to reach residual to calculate your CT requirement, the use of pH reduction will improve that, so will reduce the decay of ozone. So that is the improvement of the application. And also reduction of pH helps the coagulation and flocculation process to reduce, to get rid of the turbidity and organics. Yeah. So this is the advantages of the reduction of pH. We found it.
Now, what about with peroxide? Now, isn't there a reaction rate function of ozone and peroxide at different pH? Is it more favorable at a higher pH for that reaction rate to occur?
We didn't see much difference, to be honest with you, because the amount of we're using is quite low. When you use 10%, and when we're using ozone at 2 milligram per liter, 10% is 0.2 milligram per liter.
Yeah.
And even if you use up to the 3%, it's not much, 0.6. Compare that one, and we compared it when used with UV. And usually when we do that with the ozone prior to the treatment processes, flocculation, sedimentation, filtration. While with the UV, you put the UV after the filtration, and you put the peroxide. And the recommendations is to, for example, when you need testanode and all that, and pharmaceuticals, cyanotoxins, you need to push it up to 5 milligram per liters to 8 for the peroxide. What does that do? That reacts with the chlorine you added to have residual
you can't have
system.
Yeah.
So we found it, and we have a study was done in 2012. It shows like your THMs tripled to meet the 1 milligram per liter of chlorine in distributed system. We added 3 times the chlorine you need compared, because you're putting, and we use 5 milligram per liter compared to 0.2 milligram per liter. And we tested, we couldn't find any peroxide left at the end.
Sure.
Yeah, so that is, and at that time, there was, it presented, what made me do this study, I was at a conference, and it was presented, they were doing it at a municipality for taste and odor control. And I said, what about THMs? Oh, there's no issue. I said, I don't think so. So I did that study in Walkerton. I have 2 lanes, one with the UV and one with the ozone, with the peroxide. And it shows the data. We published the paper in 2012. Until this day, nobody challenged it.
Yeah.
Because they knew about it. But nobody told that to the customer, unfortunately.
Unfortunately.
Yeah, because when you have a paper, if you say it's working, okay, that is my opinion, and I show data, and I show residual. What we did SDS THMs, simulated distribution system, and we mimic the simulate the distribution system time of contact time, or use. And you see the THMs tripled compared to when you use ozone and peroxide. So that was a massive information. People will use it for municipal water treatment.
That's great. I really wanted to see what you thought about that. There's areas that I've got involved with that are on the industrial side. And the industrial side, we're finding, especially in the last, I don't know, 5 years, 10 years, very high level ozone doses. And so, like Saad was saying, in municipality, you're in a few milligrams per liter ozone dose. We are being challenged with systems in the hundreds of milligrams per liter dose. Even at the 500 milligrams per liter, we actually designed one system working on right now that's over a couple thousand milligrams per liter dose.
Wow.
And it's a really technical, it's a really a technical challenge to how to get that much ozone into water. And so you have to design things in ways with a lot of contact time and a lot of recirculation processes where you have certain flow dynamics that works hydraulically to make that happen. In the discussion of AOP, what I find is pH is important, as the Saad was saying, but on my side, I have to kind of make sure I have alkaline pH for that reaction rate to happen, because peroxide reacts faster at a little higher pH. In some systems, when they get too low, in this case, I don't want those to hang out too long. I need to have it react to the peroxide, otherwise they're just going to hang out together. So we do have systems where we modify that pH, to find that sweet spot, 7.5 to 8 or thereabouts. Dosing with peroxide to remove that, create those radicals. So some of these systems are really high in terms of dose to get rid of the contaminants. In the area of concern that's coming up, which I think Snell, you're asking for, what's the emergent thing coming in? What's coming on? Well, for us, in a lot of areas, is these industrial process waters from different companies. And these are pharmaceuticals, these are industrial solvent companies, they're actually are trying to clean their water up, and they're requiring very high doses. In the past, I never really looked at those as much, or the companies wouldn't go there because the cost per gallon or cost per liter of treatment is high. But now they're like, well, we need to do this. And so it's really been driven by the need to either stop paying for discharge limits or discharge, penalties and other things. Is actually being in their favor now to treat these wastewaters to get these contaminants down. One of the areas that we're hit where peroxide as a way to making radicals in AOP that's advantageous is BOD removal or BOD reduction. Okay, so now traditionally, when you partially ozonate water, and you're looking at BOD, biological oxygen demand, the 5-day biological oxygen demand, often when you partially ozonate in anywhere from 1 to 10 milligrams per liter, 15 milligrams per liter, you actually increase BOD often. And that's because those organic compounds now are been oxygenated, broken up. Oxygen N groups on them, carboxylic acid N groups, carbonate groups. They become more biologically available, more biologically.
May I interject here? And that is when you bring a treatment process prior to the ozone application, because and that is what when I designed that water for reuse, and there are different processes. You pick one, for example, with a low energy use or a high energy use.
Right.
Okay, so you reduce that, and you can do a multiple. And in my work, I included an AOP as well. And I do it after these processes when you reduce significantly, and because you have treated sewage effluent have about 5 to 6 milligram per liter at least.
Yeah.
If not more. So when you reduce that, then you do oxidation, and you follow it by biologically active filter.
That's right.
And that is that is what's in my design as well. And that's how you could reduce it. Because, just to hit it with ozone, you need 15, 20 milligram per liter ozone.
Yeah.
And also you can use the multi-stage as well.
Right.
A multi-stage application. And that is what helped. If you have to use it first, to use a small amount, but then the final hit is after reducing your DOC, BOD significantly.
It's absolutely true. In these processes, these are where you have multi-filtration aspects to it. They're complex, like Saad's saying. these are processes where you're already trying to take care of the total suspended solids. You don't want to have to ozonate those. That's, you're wasting your ozone. So we flock that out, take those suspended solids as much as possible. Even some insoluble organics that will flock out, you take those out. So we're talking about a process where that's already kind of has happened. Often we will, try to work with the customer where we can do the pre-ozonation part, which what Saad is saying, make it more biodegradable, and then followed by biological reactors, and RBCs and other things like that.
Mhm.
Sometimes that can't happen. We have customers where they don't have the space for that, or they don't want to do that way, and then that's brute force oxidation. We have one where we actually are getting rid of anywhere from up to 200 to 500 milligrams a liter BLD. I mean, actually getting rid of it through oxidation only. It's not very common, but this is one of the processes we worked on, and they have to do it because it's a dirty waste stream. That they need to take care of this BLD, and of course the only way that BLD really gets removed, through oxidation is mineralization of that organic compound to CO2.
Mhm.
Because even if it's chewed up to these smaller molecules, well, that's food for bacteria, and that's consumes oxygen when they do aerobic activity, and removing and the growth of the bacteria and removing that carbon, you're still consuming oxygen. So when you mineralize it to CO2, complete oxidation, then that really lowers that BOD down. And so there's some processes where we've had to do that, and this is where we're merging the emerging industries and so on. That's our opportunities, is solving these problems where you have high BOD. You can't always get using biological filtration afterwards, even though that's the best way to do it, the most efficient way to do it. You have to have some of these customers they need a small platform, and you have to work on this high BOD reduction. And this is where we get, into these really high level oxidation processes where you have to kind of burn that water and produce a lot of radicals. And only radicals really, ozone can only do so far. And this is where we do multiple ozonation and radical production to kind of really take those molecules that get ozonated and there are pieces left over from ozonation that no longer want to react, usually alcohols and others and aldehydes that don't want to react very well, will get chewed up by AOP, by the radicals.
Right, thank you guys. So thank you for providing me with information on the lessons that you guys have learned on the field. Just closing points here. I want to give you guys both an opportunity to talk about how you see AOP scaling over the next 5 years, and any additional comments that you want to give to decision makers or water treatment plant facilities, if you have any remarks for them. So if you guys want to just go ahead, Dr. Saeed, if you want to start with that, and then after that, we'll go with Thorn.
Well, we're waiting for guidelines, to be honest with you, because guidelines, especially for municipal operations, because, if you don't put more than toxins, and Health Canada is resisting adding toxins. They have only one they deal with, which microcystin allow. And I'm challenging them for that in my research. And I put it in my introduction when I put the proposal. This will help the federal government to review their guidelines because it's there. You don't wait till it happens. So I think, when you have regulations, then people start to apply new technologies. When in the US applied the disinfection byproducts rule, the use of ozone increased because of the THMs issues and all that. And I remember when the issue on the bromate, the EPA want to reduce bromate level from 10 to 5 back in 2005. And at that time, I went to Walkerton, and we sponsored. I put $10,000 from Walkerton into the study, and others. It was a big project, and it shows that bromate is not really carcinogen. The study showed that the enzymes neutralize the bromate. Enzymes in the stomach of the rat, neutralize it. So, and when we introduced it to the EPA, one of their senior people was at the conference. He smiled. He said, "Oh, that's very interesting." And we never heard from them after that. Nobody will say, "Okay, we made a mistake." Well, they were not making a mistake. There was an influence. The chlorine group, the UV group, and sponsoring politicians And they pushed that because it wasn't based on science,
Yeah.
the decision. So anyway, so I think, the application, and also we need to play more role in educating people, municipalities. Like I go and I've done it a few times, and I go and request to have a meeting with the city council, different my city, different cities, and I put the cards on the table. There's now one group on the Great Lakes. They were using just advances, and their intake is in the middle of the algal bloom. And I showed them the satellite pictures. I said to them, it's not if, it's when you're going to have the problem.
Mm-hmm.
So, and I showed them what happened in Toledo. Many of those people don't follow these details. So I think, with guidelines and education, I think we're going to bring more people, and also investing in the new people. And that is where, because those people are going to be in consulting groups, municipalities, government, and that's where the application is going to come.
Mm-hmm.
But the thing is, I believe in the science, and my main interest is safe drinking water to the public.
Right.
And that's the biggest thing.
Yeah.
Worth more than money. Yeah.
Yeah, thoroughly agree.
Yeah.
I think from my side,
Mhm.
the opportunities are really in tackling all the subjects that Saad said on the cyanotoxins, on pharmaceuticals, and what we call forever chemicals is a big deal, like PFAS and so on. And I think ozone has a place in there, and especially ozone AOP has a place. There's a lot more to be done, but there's a place for it there. So I think in the emerging challenges we have, Saad said about guidelines, there are things like that that have to be put in place in legislation to really push these companies to want to have to deal with it. Unfortunately, a lot of times it's that way, where it becomes financially painful in one form or another if you don't handle these problems. And unfortunately, so many times you have to have something in place like that in order to have companies, okay, we'll take a look at these things, or municipalities, and change our rules and start looking at these problems on a technical and science-based way to solve them. And I think ozone really has a tremendous opportunity, especially in advanced oxidation, in handling some of those really challenging forever chemicals that we have. There are other technologies that are being looked at. Nanobubble technology, for example, has a place in there. That's really very cool, and ozone's combined with that too. And that's some really interesting science and very interesting physics is happening with nanobubbles. I think it's quite fascinating. With oxidation and
what we call it the multi-barrier system.
Mm-hmm.
A multi-barrier system. No, there is no silver bullet.
That's right. That's right.
Okay.
There is not. This, and so the segue from that to the up and coming professionals. One of my recommendations is to be multidisciplinary as much as possible. In other words, we like to dive deep into our discipline, which is good. We need to be experts at what we are, but we also need to broaden our experience across the field because, as Saad was saying, in our experiences, there's many different technologies that usually will need to be combined to find an overall solution.
Mhm.
It's not just one technology. You have to learn how to apply. Do you need to be, proficient in filtration systems and hydrodynamic flows and chemistry? There's physics involved with it. There's biological things involved with it. And understanding all these processes that are across can really give you a good overall view of looking at problems and seeing what's the best way to solve these. Which tool do I need to take out of my toolbox to handle these problems and come up with the best solution possible. Sometimes we don't have the answer, and so research. And so I'm a big proponent for research, to delving deep into it to figure out, okay, well, what's the better way of doing this? Or maybe we need to understand this a little bit better so that we can apply the research into understanding this particular chemical or the forever chemical, whatever it is that we're looking at, and what's the best way to tackle it, because it's complex. As simple as that water molecule is, it's just two hydrogens, one oxygen. Water is complex, and it's a source of all life. And I like what Saad said about drinking water and municipal. This is water that's feeding and hydrating the country and the world, and having clean water, the best that we know how for everyone, is extremely important, because it's, for longevity, it's for health, and for society itself, and not only just for humanity, that we want to do something that keeps the water as clean as we can and keep pushing that envelope. The addition of science behind water has many great successes. The removal of waterborne organisms from just chlorination itself save millions and millions of lives by itself, by that technology. Adding ozone is paramount to understanding how we can make that water better in many ways, and not just only for drinking water, but for wastewaters as well, because that's one of the biggest things we have is pollution and the problems that handle the back end of industry, where we need to look at the back end and say, okay, how do we handle what's coming from these? We can't stop these things from happening. We can improve processes in industry and manufacturing, but we're always going to have some waste. And how do you handle that? And so this is a part that we believe that I firmly believe that ozone and oxidation technology has a place. And education, like Saad said, is extremely important. And I can't speak more highly about the importance of the emerging training and education of the next generation coming forward. Because we're both getting a little bit older now, and and our age, right? And we want people to stand on our shoulders to go higher and better and improve what we have for our environment.
Leadership will be able to watch and actually understand AOP and actually try to implement it. I think that's the goal at the end of the day. So at the Pinnacle Academy here, we are committed in providing this insight, providing a forward-looking. Our goal here is to talk about this, understand it, understand where ozone and AOP is heading, and why it matters more than ever. So thank you everyone for joining us. We'll provide this moving forward. And if you guys have any thoughts, always please feel free to reach out on LinkedIn or reach out to us on our website. We can definitely add on to additional questions that people do have. Thank you so much.